Thank you. Okay. Thanks to organizers for the invitation and possibility to speak at this remarkable seminar. I will start with inverse spectral method. I will follow the work by Krichever of 2002, at least at first steps of my presentation. So, following to Krichever, the GLN Hitchin system can be defined as follows. There is certain geometrical data, Riemann surface sigma. It's drawn here in the right upper corner. A holomorphic differential xi and its zeros pi. The number of zeros is equal certainly to 2 double G minus 2, where G is the genus of the Riemann surface. Now, we assume that a certain Lie algebra is given in Krichevers. By Krichevers idea, it should be full linear algebra of size n. Then we fix n g points on the Riemann surface, and the points gamma 1 and so on, gamma n g. And to every such point, we associate an n-dimensional vector alpha, which we regard as to a column. I try to draw them here like such columns. Okay, and then the Lax operator of the Hitchin systems of the Hitchin system with structure algebra GLN or structure group GLN is defined as a meromorphic map from our punctured Riemann surface to the Lie algebra GLN. This means that this is a meromorphic matrix value function on the Riemann surface. It's required that these functions is allowed to have poles only at zeros of our chosen differential xi at p1 and so on, p2 double g minus 2, and also as the points gamma 1 and so on, gamma and g, and nowhere else. At the points p1 and so on, at the p points, there is no restriction on the order of pole, but at the points gamma 1 and so on, at the gamma points, the expansion of L of Z is specified as it is written here. It's written that at the point gamma with local coordinate Z gamma, L should have residue of the following form: certain vector beta multiplied by vector alpha transposed, which means that this is if we regard to beta as to vector column and similarly to alpha, then there is a rank 1 quadratic matrix in the numerator. we also require that vector alpha is an eigenvector for the term L0 with some eigenvalue kappa. Okay. The set of the points gammas and associated vectors alpha is referred to as Turing parameters for the reason that they come from Turing's work on parameterization of holomorphic vector bundles. Well, now hierarchy of equations of Hitchin system by following idea by Igor Krichever is defined as follows. It is defined by Lax equations. L point is equal to commutator Lm, where L is as above, and M looks similar, is defined similarly, with the difference that there is no restriction on on the nominator of the degree -1 term, and no relation between mu and m0. Let me return for a moment to the previous slide. Beta and alpha are related with the condition equivalent to the requirement that the trace of this matrix is equal to 0 here. About eigenvector condition, I already said, but for M operator, this requirement are omitted. These requirements are omitted. Now we define the subspace of all L operators distinguished by the condition that divisor of L plus divisor of plus 0 divisor of our fixed holomorphic differential psi plus divisor of gamma points is non-negative. This space, again, following to Krichever's idea, serves as a phase space of our Hitchin system in this presentation. Okay. In order to really obtain an equation here, we must relate L and M some way, and they are related by the following theorem. For a generic L, there is a family of M operators labeled by letter A, where A denotes a triple consisting of a point consisting of one of zeros of our fixed holomorphic differential psi and two integers where n is positive. M is not less than pole order, is not less than negative to order of 0 of the differential psi. So for each such A, there exists and unique up to normalization such operator MA, which has a pole only at gamma points and one of p, and at this pi, and in the neighborhood of this pi has the following expansion relating m and ma and L. Here, wi is a local parameter in the neighborhood of pi, and m, L are taken from here. Okay. The statement is that the equations, first, that such m operator is exists and is unique, and the second, but not the least, that equations DAL equal to commutator LMA define a family of commuting flows on the space L psi. Here, dA is time derivative along corresponding to the time TA, just the parameter of the flow. Good. So are there questions so far or not? If not, then I continue.
Yes, it's okay. Please.
Okay, good. Now we said the eigenvalue problem. It's quite natural. Here Q is a point of our Riemann surface. T is time. Everything else is okay. Good. Capital Q is a pair consisting of small q and the corresponding eigenvalue, which tends to be Q tends to be a point of future spectral curve. Spectral curve is defined sigma overhead. How to say head sigma? I don't know. Spectral curve is defined by the equation, by a characteristic equation of the operator L. L. Good, and it's it's a Riemann surface of algebraic function given by this equation. It certainly doesn't depend on t, and let's observe that by Lax's
Sorry, Oleg. What do you mean by it does not depend on t?
What I mean that what?
So it depends on t or not? Sorry, I didn't get it.
Coefficients of spectral curve are integrals of the system. It is what I mean.
Okay. So it does it depend on the parameter t here?
No, it does not.
Does not. Okay.
L itself depends on time, but spectral curve does not depend.
Okay.
Well, now by Lax equations, by these Lax equations, these two operators compute L and GA minus M A. Hence, psi, the eigenvalue function of L, is also an eigenvalue function for dA minus MA with some different eigenvalue, which I denote also following to Krichever by FA. Good. Psi and Fa are meromorphic functions on the spectral curve. Psi is a vector function, Fa is a scalar valued function. It is important property of psi that its pole divisor is dynamical. For this reason, it's normally is called dynamical divisor of the problem. Now, in particular, psi has poles at gamma points. At gamma points, I don't prove it now, but believe me, it's true. Let me ask you to believe me that it's true. And evolution of the point gamma is governed by this differential equation, that time derivative of the coordinate of gamma is equal to such scalar product of mu, which comes from M operator. Let me show you. Mu comes from the definition of M operator. And what's known that the nominator, which is a vector column, is proportional to alpha. Okay. Now, the appearance of Baker-Akhieser functions is called to existence by the following wish, by which that eigenfunction wouldn't have dynamical pole divisors. By theory of Krichever, which is very universal, it is sufficient to, in order to get rid of dynamical pole divisor, it is sufficient to multiply the eigenfunction, vector function psi by the following scalar valued exponent. Exponent of the integral of the function fa, to variable upper limit, ta. Let me remind that fa comes from the eigenvalue problem for ma. Here it appeared, fa. Okay.
So, a naive question. After you take the exponential, why you can still get a meromorphic function?
It is not a meromorphic function anymore, and this is what I would like to state now. It is meromorphic. It is meromorphic. Yes, it is meromorphic outside divisor of our fixed holomorphic differential. But at the points, at zeros of this holomorphic differential, it has exponential singularities. Depending on time, this way. I'm not sure that where W is a local parameter, there is in the power there is degree. Sorry. There is a summation in triples P Mn by M of A and N of A. I denoted these two integers which correspond to the triple A, which are involved to to the definition of the triple A. So the theorem of fundamental theorem by Krichever is that the pole divisor of this function hat psi hat is static, is time invariant. And there is a existence and uniqueness theorem that for any divisor of degree equal to genus of the spectral curve minus dimension of our Lie algebra plus 1, and any set of exponents of such form there exists and is unique under certain normalization conditions. The Baker-Akhieser function exists and is unique under certain normalization conditions. So let me say once more that by Baker-Akhieser function we mean here the function meromorphic outside certain divisor, where it has exponential singularities. Good. How to find out explicit solution using Baker-Akhieser function? This is content of inverse spectral method. So assume we have a Baker-Akhieser function psi hat. It's a function of on the spectral curve. So a function of a point Q on the base Riemann surface, and eigenvalues and eigenvalues lambda such that points Q lambda 1, Q and so on, Q lambda n are located over the point Q, are pre-images of the point Q in the covering which is the spectral curve over base curve is a covering of the base curve with pre-images lambda 1 and so on lambda n over the point Q. Good. And take the point Q, take its pre-images at the spectral curve. We obtain n vectors, depending on Q, and we form matrix psi capital considering this psi hat as psi hat of Q lambda J as columns of this capital psi. Now everything is proved by Igor Krichever that L and MA can be restored by the following explicit formula. L is psi lambda, psi 2 minus 1. MA is dA derivative of psi by psi 2 minus 1 negative. Where lambda is diagonal matrix formed by these eigenvalues. So we have spectrum organize it into the diagonal matrix and conjugate by the matrix constructed using Baker-Akhieser function, and find out L and MA for every A in terms of Baker-Akhieser function. I will not write it here and somehow show it, but there is a formula going back to its and developed by Igor Krichever, which gives explicit expression of psi hat via theta functions, and by that we by means of its Krichever formula we can obtain explicit formulas for L and MA in terms of theta functions. Now let's pass to the case of simple groups. For example, consider SON. Then the construction of the Lax operator is the same as for GLN, with two exceptions. First, Lax operator is a meromorphic map of the base Riemann surface to the Lie algebra of skew-symmetric matrices, SON. The expansions of Lax operator and M operators at a gamma point is of the following form. We put instead of alpha beta, we put the easiest rank 2 skew-symmetric matrix in the nominator of the degree -1 term. Now the relations between beta and alpha, L0 and alpha are the same as for GLN, but additionally, the following requirement to alpha appears, which is quite natural and appears also in flex theory and at other points. Well, now abstraction. What makes it possible to parameterize Baker-Akhieser functions and hence the solutions is time invariance of their pole divisors. We explain, I will explain now that the time invariance of divisor takes place for GLN and does not for SOM and other simple groups.
Oleg Karlovich, I'm sorry, could you return to the previous page?
Yes.
Alpha T alpha.
Alpha T alpha, yes.
It's not given that alpha is 0.
No, it's complex. It's complex
Okay.
relation. Okay.
Excuse me.
Okay. It's just codimension 1 condition. Well, I said earlier that psi the eigenfunction has a pole, but let me make a look that I don't know that. Let me assume only that it has certain expansion which starts with degree m, positive or negative, or positive or negative. But I still assume that A gamma is proportional to alpha, and hence the scalar product of A gamma and alpha gamma is equal to 0 by that condition, which we discussed right now. Okay. Besides, let me recall that Z gamma is the evolution of Z gamma is governed by these simple differential equations where mu A comes from the M operator. Well, then the equation, the eigenvalue problem for the operator dA minus MA looks as follows. Here is the -1 term, degree -1 term of MA. Here is the beginning of the expansion for psi. Well, let's compute leading terms on the left and on the right hand sides. The leading term on the left hand side is presented in the bottom line. Is presented at the bottom line. Indeed, if we multiply this term m mu a alpha t by A gamma, we will obtain 0 because alpha t by A gamma is 0. So only only this term is essential. Only this term, only the derivative of the first term of psi and the product of this term by the first term of psi are of significance, of significance. I don't know. So by simple calculations, using this relation for evolution of the gamma, we obtain that the leading term has the following form, where m times what's written here comes from the derivative, and this +1 comes from multiplications of the residue by the first term of psi. All in all, we obtain something of order m-1. Good. But it implies that FA should have a pole at the point Z gamma, because this order is M, but we must obtain something of order m-1. Hence, FA has a pole. We write down this relation expresses this fact that FA has a simple pole, and f-1 from the previous, it follows that f-1 is equal to this expression. Again, altogether, we have logarithmic derivative of z minus z gamma. This is the expression of for fa, its logarithm up to higher terms, and we easily can integrate it in order to obtain Baker-Akhieser function from psi. We should integrate it. We easily do it and obtain z minus z gamma to minus m plus 1. Okay, good. And we have that Baker-Akhieser function is obliged to have a simple pole at every gamma point. So dynamical poles for Baker-Akhieser functions are unavoidable. And for this reason, all the construction with Baker-Akhieser function is destroyed. This is the first, this is what I call the obstruction for inverse spectral method in case of Hitchin systems with simple structure groups. Now let me tell you. So the first part of my talk is over, and the second part will be devoted to the following circumstance, that certain abstraction exists also for Hitchin for separation of variable technique for Hitchin systems. It doesn't, there is no abstraction. Again, there is will be no abstraction in the case of GLN, but there is some in the case of simple groups. Now, I must speed up because I have only 20 minutes left, about 20 minutes left. So, first of all, let me define Hitchin system in different way using the method of separation of variables. Let me write down the spectral curve in such form where L is again meromorphic function with L is again meromorphic function which is G valued, and G is one of classicals is either GLN or some orthogonal or symplectic Lie algebra. D is the dimension of the standard representation of G, and N is the rank of our Lie algebra. Now, numbers dj are nothing but degrees of basis invariance of the Lie algebra G, and again, and by D capital, we denote the divisor of our fixed differential psi, holomorphic differential psi. just examples for symplectic Lie algebra of rank n. D is 2n for for Lie algebra of skew-symmetric odd dimensional Lie algebra. Rank is again n. Dimension is double n plus 1. It is easy proposition that that the coefficients of the spectral curve have poles of order no more than orders dj, the degrees dj of the basis invariance of the Lie algebra G. And now, if we specify the class of base curves, we can we can find out a basis in this space O of minus dj capital D. This is the only non-effective point at Hitchin's construction of his systems, and it can be this non-effectiveness can be avoided if we just specify the class of base curves. The easiest case is the class of hyperelliptic curves, and just for simplicity, I consider only A and B and C and root systems for structure groups, and don't speak now about Dn and exceptional systems. So we take hyperelliptic curve and natural holomorphic differential psi. Then we know the degree of the divisor of its zeros, and the proposition is the following: a base in the space of the base in this space is the following. It's given by degrees of x and degrees of again degrees of x in different limits multiplied by y, where x, y are just functions on our hyperelliptic curve. Let's write down the equation of the spectral curves in this form. It is obtained by expansion, by taking expansions of these coefficients Rj, sorry, Rj over the just found base. And coefficients are with certain coefficients which we denote as h with certain indices written here. Now we would like to point out separating variables for this separating variables for Hitchin systems, for all Hitchin systems. For that, we give the spectral curve by means of a tuple or set of points it passes through. Let H be the number of these points. The easy proposition, the easy statement is the following, that the number of these points is equal to the product of the dimension of the corresponding Lie algebra by genus of the base curve -1. This is true for simple algebras. For Gillian, it's a little bit different. Up to it's a little bit different. Let me skip it now. The proof of this formula, the proof of this relation amounts to the well-known relation in the theory of simple Lie algebras that the sum of double dj minus 1 over j from 1 to the rank is equal to the dimension of the Lie algebra. Now the system, now Hitchin system can be defined as follows: phase space consists of the sets lambda 1 x1 y1 to lambda h xh yh subject to the relation of the hyperelliptic curve. Poisson bracket is defined like this by this formula, and Hamiltonians are defined from the system of linear equations expressing the fact that our spectral curve passes through the points lambda x y. So we have observed also that at every triple lambda x y, only two parameters are independent because x and y are related. Why this system is the system is integrable? It follows from the simple lemma, which I would like to omit, simple analytic lemma, which I would like to skip because I miss time actually. Well, now I also skip the general method of generating functions. The aim of this method is to complete coordinates h, j, coordinates h, j to the canonical system of coordinates by means finding of dual coordinates phi j. The prescriptions the prescription given by classicists of separation of variable method, which are Hamilton, Jacobi, Arnold, and Evgeny Sklenin, who is present here, still present here, I guess, I hope. The prescription is the following. In order to obtain phi j is obtained by as a following sum of integrals, the following sum of integrals, where okay, all notation are already invented. Well, let me just explain. H coordinate Hamiltonians H are expressed via XY via triples XYL. These are just partial derivatives of the equation of spectral curve in its coefficients aj and lambda. Let me show this. So this is okay. So the derivatives there are derivative of r in lambda and in hj. I just replaced this complicated index gk0 or gs1 by one letter there. Well, and taking account of the explicit form of the spectral curve, we obtain the following explicit formulas for Darboux coordinates. These are h and phi, where phi are given by this at first glance complicated relations, but in fact, idea of that relations is not complicated at all, because the following theorem states that these integrands form a base of holomorphic differentials on the spectral curve for the system RAN, and a base of holomorphic prime differentials for the systems A1, B, and Cn. Let me explain that the systems A1, B, and Cn are distinguished by the fact that their spectral curves possess the involutions. Lambda are invariant with respect to involution lambda to minus lambda. And prime differentials are differentials skew invariant with respect to this involution. Now we conclude from this theorem, from the last theorem, that the map which takes the points of our phase space to points phi is nothing but Abel or Abel prime transformation. It's Abel transformation of the symmetric power of the spectral curve to Jacobian in the case of G равно GLN, and Abel prime transformation to the Priman of the phase space to the Priman in case of simple groups. And we have obtained in this easy way by method of separation of variables that Hitchin trajectories are straight lines on the Jacobian or Priman of the spectral curve. Sorry, I didn't explain why they are straight lines, but let me return. It's because the symplectic form of the system is canonical in the coordinates h and phi. Okay, they are straight lines. but all Liouville integrable systems look the same. Look the same on their invariant theory. For this reason, we would like to find out Hitchin trajectories in the original coordinates xy, y, xi, yi, and y. For that, we need to reverse the Abel or Abel-Prim map. In the case GLN, it is possible and amounts to Jacobi inversion problem. In principle, okay, if we would have such inversion in all cases, the problem would be resolved completely. We just take a straight line on the abelian, on one of these abelian varieties, and send it back to coordinates xy lambda by the inverse transformation. Unfortunately, it's not always possible. In principle, the Jacobi inversion problem can be resolved by means of the Riemann theorem. If theta denotes the theta function of the Jacobian, or Riemann theta function, then the preimage of any point of Jacobian is given by the set of zeros of the function of such functions constructed by means of theta function, Abel transformation, and Riemann constants. P here is a point of the Riemann surface, in our case of the spectral curve. And it's known by Riemann theorem that the preimage consists of exactly H points, where H is dimension of the Jacobian. There is also a way for effective solution of the problem, in particular giving the Hitchin trajectories via theta functions in the case of G equal to GLN. Unfortunately, I will not have time to show the last slide with the corresponding formula. But let's focus on the obstruction for simple group. For simple structure groups, the trajectories are straight lines on premians versus Jacobian. And as I see, there is no solution of the inversion problem on premians. Indeed, if theta is a prime theta function or theta function of the prime variety, then the number of zeros of the same function f of p as above is equal to double h, where h is the dimension of the premian. And but the solution in the original coordinates x, y, lambda should consist of h points. We need h points, but analog of Riemann theorem returns us double h points, and these double h points normally are in generic position. There is no way to distinguish somehow h points, or group this double h points into pairs using convolution. It's impossible. All that follows from lemma due to Fay, or maybe only just presented in the book of Fay theta functions on Riemann surfaces. I gave the exact number of the corresponding statements. This makes a problem. This is abstraction for resolving Hitchin systems by separation of variable technique. But let me, my time is over, exactly over now, but let me say that I don't believe that these two abstractions could not be overcome. I believe someone will find a solution in this way. Thank you very much.
Oleg Karlovich, thank you very much for optimistic talk. Are there any questions? Me, I have some questions. In particular, was your choice of Poisson structure in separated variable crucial? In the
Sorry, Dima, it's quite, I hear you quite bad. The sound is quite silent. I don't know the reason.
My question was about the choice of the Poisson structure in separated variable. So is it crucial or it's just
choice of Poisson structure? I have written there in the slide that this is a subject of special discussion. It follows there would it follows from the known it follows from the known expression for action angle variables, and I would need extra 2 or 3 slides to explain it. For the, it can be proven. It can be just derived from the known expression for angle action angle variables.
So it's not particular choice. So it's okay. It's not a choice. No, it's not a choice at all. It follows from something. Okay. Another question about the integrable systems related with the orthogonal group. So by the first view, I thought that it's the real algebra, but in fact, it is essentially complex.
Everything is complex here.
Complex. Yeah. But however, is it related with? Are there some Hitchin models over orthogonal group related to the geometry of Leg varieties? So my first example is the Toda chain and full Toda system, which is essentially geometric by the origin. So do you heard something about more general Hitchin system related with this group?
It's not really done, but there exists certain generalization of Turing approach to description of Turing approach to classification of holomorphic bundles, and there emerge certain flag constructions instead as a generalization. But are there any integrable systems related to these generalized bundles? I don't know.
Thank you very much. If there are no other questions, I'd like to thank you.
Sorry, if it's all right to jump in, I have a quick question.
Yes.
Just at the end of there, I sort of lost where you introduced your Primian variety. What involution is giving you the prim there rather than Jacobian?
What is the relation?
What involution? I mean, I'd expect the prim variety to come from sort of an involution on your curve. and I didn't spot where in your sort of computation that came in, why you ended up on the prim rather than the Jacobian.
Before I reply, I would like to discuss whether I understood you correct. Sorry,
That's fine.
I switched to Russian for a moment. Дима, вопрос о связи премиана и якобиана?
Нет, мне кажется, надо уточнить еще.
Надо уточнить, да?
Ага.
Okay, let me start. Let me start to reply. But if I will reply different question, please correct me. Premian. Okay, Premian is just a subvariety of Jacobian. It's just a subvariety of Jacobian, skew invariant with respect to the involution coming from the involution on the Riemann surface. Is it relevant to your question or not?
Yeah, that is relevant, and the question itself was, you as you correctly say, the premium is the skew part with respect to this involution.
Yes.
And I didn't see where in your slides which involution you were taking. Is it just because?
Okay. Okay. I will try to show you. Only here. I said integrands. When we we are finding Darboux coordinates, which are h and phi. So phi's are given by these relations, and integrands of these relations are just all basis holomorphic differentials in case of GLN, and prim differentials for orthogonal and symplectic groups. And premium is taken with respect to this involution on the spectral curve. The point is that for simple groups, the spectral curve, the equation of the spectral curve contains only even degrees, even powers of lambda. For this reason, it's invariant with respect to this involution, and there emerged prim variety instead of Jacobian. Now, had I replied your question or not?
Yeah, that's brilliant. Thank you. Do you have a sort of an understanding or sort of a feeling of why it should be in the prim in this case? I mean, I suppose when I think of my own work, I sort of don't yet have an intuition for why certain flows should lie in the prim or not, other than obviously just knowing the calculation. So I don't know if you sort of have a sense here of why it should be the prim.
Yes. Okay. No, it's prim and not with respect to y. It's prim and with respect to lambda. Yeah.
Oh yeah, no. So why in the word why, as a what is the interpretation? Do you have an intuition for why?
Sorry. Again, I don't understand the question. Дим, вы понимаете вопрос? Я не понимаю.
Yes, because the model is invariant with some, so it's related to, for example, orthogonal group with.
Yeah, if there is a simple group, there is always certain involution, just Cartan involution. Cartan involution in the Lie algebra. It is a reason of emergence in involution of the spectral curve. This lambda to minus lambda is just a consequence of presence of Cartan involution in the Lie algebra.
Yes.
Yeah, I suppose, and sort of sorry, keep dragging this on, but I suppose, you know, this involution, it picks out the prim subvariety, but there also is the Jacobian of the quotient curve also as a subvariety. And so there's sort of two distinguished subvarieties. And so I think at least a priori, it's not clear which one of these distinguished subvarieties you'd expect it to flow in.
Okay. Okay, but we just by calculation, just method of generating functions gives us certain expressions for integrands, and these expressions are skew-symmetric, not symmetric. And this is the reason of appearing the prim variety.
Sure. Cheers.
Okay.
Yeah.
Yes.
Thank you.
Okay.
Yeah, I suppose that I have no other questions, and I'd like to thank you once again, and to wish all of us good time and good mathematics.
Okay. Thank you very much for attention. Thanks. Goodbye.
Bye.